All right, so test 4 is going to be next Tuesday. Next Tuesday is the 24th of November, so it is the last day of the semester. The study guide is on Canvas, so whatever I do not, or when I finish, if there's anything that you think is missing or you need more assistance on, then you should check out the study guide that's available on Canvas. The test will cover Chapter 7, Chapter 8, and then Chapter 9 and 10. I merged them together. I lectured them as one unit. And the test will be 25 multiple choice questions, and then that's it. Okay, 25 multiple choice. No, there will not be a problem set. All right, so that's the main thing. That should be your focal point for next Tuesday. I just never had the time to do a problem set, so just so much stuff going on. Other things, my system is anytime we have a test, the quiz will be due on the same day. So quiz 4 will be due on that day, the 24th, which is next Tuesday. Make sure you turn in all your lab reports now. Okay. Like I told the previous section, and I also emailed them in the announcements, if you look at your Canvas gradebook and you see some blanks, okay, come next week I'll put those blanks, I'll fill them in with zeros if there's no assignment there. Once those zeros go in there, you'll see your grade, your unofficial grade, will drop. So make sure you turn in everything that needs to be turned in. Particularly with the lab reports, there's a lot of students who have not turned in a lab report, maybe around, I don't know, half the class. All of the lab reports. And then turn in your lab notebook. If you've taken the lab and done the lab, you can turn in the lab report. Just put it in Friday on my desk or in my office door. Okay. So some of you have done that already, so thank you, and I'll put in the points on Canvas. All right, so let's just go over some of these 25 questions that will be on your exam. The first thing has to involve, will involve electromagnetic radiation. So this is Chapter 7 material, electromagnetic radiation, also the electromagnetic spectrum. All right, the electromagnetic spectrum is, as stated, basically a spectrum. Okay, so on one end of the spectrum, you'll have very high energy, okay, high energy radiation, like your X-rays and gamma rays. Okay, so we'll call this high energy, things that could really do harm. If you push it up to a certain level of intensity and energy, so the higher the frequency, I'm going to call frequency V, and the lower the wavelength, lambda, we're going to call that the high energy end, because remember, this is an entire continuum. Okay, so that's one end, all right. All the way on the other end, we have kind of the low energy sector of the spectrum. Okay. The low energy spectrum, kind of things that are relatively harmless. Okay, AM, FM, radio waves, they have energy, but they're not going to really do any harm to you. Okay, at least I don't think there's any negative effects of audio waves, okay, that type of spectrum. So we're going to call this the low energy end. Low energy end is the opposite of this, right? So there's low frequency, and then there's high wavelength for these guys. Oh, thank you. Sorry about that. So low frequency and then a high wavelength for these guys. Right, so you have one end and then you have another end. And then you have things that are kind of in the middle, okay, like your UV, your infrared radiation, microwave radiation. All of those things are kind of in the middle, all right? So not too high, not too low. There's even a region here that you can see. Okay, that's called the visible region of the electromagnetic spectrum. Okay, there's a tiny, tiny little sliver. Okay, we'll call that the visible region. It's the visible region, white light. Okay, and that white light actually has 7 parts to it, 7 different wavelengths, 7 different frequencies, 7 different energies, and it's Roy G. Biv is how it goes. Okay, red, orange, yellow, green, blue, indigo, and violet. So there's a part that we can see, okay? And then, like I said before, UV, microwave, okay, infrared radiation, all of those things are somewhere in between, okay, somewhere here in terms of frequency and wavelength. All right, so 2 equations here that are important when we're looking at the electromagnetic spectrum. One is that these guys have energy, okay? Obviously, if you had an X-ray, you know about that, you know about that energy. So energy is in this equation, E equals hv. Okay, V is your frequency, H is Planck's constant. Okay, so the energy usually comes in the form of quanta packets. Okay, remember quanta packets for those that came to the lecture, the idea of quanta, okay, these little energy packets. Right, so that's one equation here, the energy, okay? The energy in this electromagnetic radiation. Some of it's kind of bad, okay, some of it is harmless, and then you have everything in between. Again, some of it's things that we can see. Right? So H is Planck's constant. I'll give you Planck's constant on the exam. The second equation that's important for you guys to know and recognize is this, lambda wavelength times frequency v is equal to the speed of light c. Okay, so these guys here on this spectrum travel at the speed of light. Okay, and the speed of light c is 3 times 10 to the 8 meters per second. So that's a constant. I'll give that to you. H is Planck's constant. I'll give this to you as well, and it's about 6.63 times 10 to the minus 34 joules times seconds. Not something you need to memorize, but it's a constant that tells you how much energy is involved in these different areas of the electromagnetic spectrum. Right, so these are 2 important equations here. And another aspect of things that lie inside the electromagnetic spectrum, another important aspect or another important characteristic is that these are actually waves, but they're actually 2 waves. Okay, they're traveling perpendicular to one another. All right, so we have one wave that's going this way. So I'm going to call that the electric field wave. I'll call that E with a little vector symbol. Okay, that's the electric field wave. And then traveling perpendicular to that is the B field wave, the magnetic field wave. So they're going perpendicular to one another. So if you can imagine in your mind's eyes the black wave and the green wave being perpendicular to one another. Okay, so this in the green we'll call the magnetic field wave. Energy in the electromagnetic spectrum is actually 2 waves traveling perpendicular. Okay, the key word here is perpendicular, not parallel, but perpendicular. Okay. B field wave and electric field wave. There's energy. You should know this just intuitively, okay, from life experience. Okay, energy in this spectrum can be very high energy, like your X-rays. They could be harmless, like AM, FM, radio waves. And there could be regions that we can see, and there's regions that we can use, like UV and microwave. The whole continuum is right here. Okay. Again, it's B field and E field that are traveling perpendicularly. It's important that you know they're traveling perpendicular. But as an example, let's say you have red light. Okay, you're driving to work and you or school, and then you come across a traffic light. You see a red light, and that red light has, let's just say, I'll throw a number out. That red light has a wavelength of 700 nanometers. Okay. You're driving, you hit a stop sign or red light, traffic signal. Okay, red flashlight, red light comes to your eyes. Okay, that wavelength we know is about 700 nanometers. So what is the energy that you're getting? Okay, that your eyeballs are getting. So what is the energy associated with this light? It's a question. So let's see if we can answer this. First of all, 700 nanometers, that will be our designated wavelength, lambda. Okay. The first thing I would do is convert this nanometers to meters. Okay, right, Elena and all. Okay, convert this nanometers to meters. So we have 700 nanometers. All right, the conversion is this. 1 nanometer is 1 times 10 to the minus 9 meters. Okay, so that's the conversion factors that you guys should know. Okay, the nanometers cancel. So this gives us 7 times 10 to the minus 7 meters. Okay, so I'm converting it to customary units of meters. Okay. So that's the red light. It's coming to you at this wavelength, just converting nanometers to meters. Okay, what is the energy associated with this? We have the wavelength. Let's go ahead and calculate the frequency of that radiation of red light. So lambda times v is equal to c. These guys travel at the speed of light. So c over lambda should equal to my frequency v. Right, c is a constant which I will give you. It's going to be 3 times 10 to the 8 meters per second. Okay, lambda is the wavelength that we've just converted to meters. So it's going to be 7 times 10 to the minus 7 meters. Okay. So the meters cancel. So let's do this on our calculator here. 3 times 10 to the 8, okay, 3 followed by 8 zeros, divided by, I like putting parentheses, 7 exponent minus 7, 7 times 10 to the minus 7. So doing that on my calculator, I'm getting an answer of about 4.29 times 10 to the 14. The units here are hertz. Okay, hertz, which is 1 over seconds. That's your customary and standard unit of frequency, hertz. Definitely you'll see this a lot. Okay, AM, FM radio, 98.5 megahertz. Okay. So hertz is equal to 1 over seconds as a unit. All right, I got my frequency V. And I think we can plug that in here into this equation to get our energy, which is what the problem that I gave you is asking for. So energy is equal to 6.63 times 10 to the minus 34 joules times second, times V is going to be 4.29 times 10 to the 14 hertz, which is the same thing as 1 over second. Hertz is the same thing as 1 over second. Hertz is the same thing as 1 over second. And then the second and seconds cancel. So let's do this on our calculator. 4.29 times 10 to the 14 times Planck's constant, which is something I'll give you, so do not memorize it. 6.63 exponent minus 34. Okay, close the parentheses. And I'm getting 2.84 times 10 to the minus 19 joules. So very, very low amount of energy coming to your eyes from this red light. Doubt it will really harm you. Okay, right? So 2.84 times 10 to the minus 19 joules. And that would be an answer that you would put on the exam. Okay, it's multiple choice, but that would be the pipeline. That would be the flow through, or how you get to the answer. One more thing I want to mention, a major theme here, you guys, is that electrons or radiation of this sort, photons, which are light particles of light, they're not just waves, but they're also particles. So a main theme here is this wave-particle duality. Is it a wave? Yes. Is it a particle? Yes. Does it display behaviors of both? Yes. Okay. Wave-particle duality. When we're talking about this stuff, electrons, radiation, light, it's both a wave and both a particle. Questions or comments on this type of problem? Okay. They travel perpendicular, E and B, electric field and magnetic field wave, entire spectrum. Okay, there's energy with each of these individual radiations, and they travel at the speed of light. Thing I want to talk to you guys about is this idea and this concept of excitation and emission. So if I draw a little graph here, okay, and I'll have energy on my y-axis. All right, you see inside an atom, okay, we have energy levels. Okay, like a video game, or like the rows of this desk. Energy level 1, that's you guys, Elena and Alex. Energy level 2, energy level 3, energy level 4, 5, 6, away from the nucleus. Okay, so in this atom, so we have energy level 1. We'll call that n equals 1. Okay, and then there's an n equals 2. Okay, you guys are n equals 3. N equals 4, so on and so forth. Okay. Higher and higher energy levels as we go to higher and higher energy levels. Okay, let's say we have an electron here, okay, by that red dot. And what we can do to that electron is we can hit it with a quanta, okay, sort of excite it. We can hit it with a quanta. Okay, so sort of bam, okay, a quanta we hit it with. And what happens is that if it's just the right amount of energy, just the right amount of quanta, you can get this excited. So let's have this get excited to energy level 4, okay, within the atom. So now we have a process known as excitation. What happens after excitation? Okay, what happens after something gets excited? What will it do? It will crash down. Okay, it will crash down back to ground state. Okay, we call that crashing down relaxation. Okay, it will relax. Okay, so after you get excited, kind of like a child. Okay, the child gets all hyped up, excited, he jumps up and down. And what happens? It relaxes back to the ground state. Okay, so this going down back to the ground state is called relaxation. But something happens when it relaxes. What happens during the relaxation back to ground state?
It has to give off energy.
Yeah, perfect. Very nicely said. Okay. When it relaxes back to the ground state, it emits. Okay, so there is emission. And Alex is right. So there is an emission, and the emission, there's a give off of energy. Very good. But what type of energy will it give off? It will give off energy from the electromagnetic spectrum. It can give off energy in any of these parts. Okay, so it gives off energy from the electromagnetic spectrum. So it could give off energy in the UV region. Okay, that's possible. It can give off energy in the IR region. That's possible. Okay, you can give off regions. It depends. Okay, everything is depends. You can give off energy in the microwave. And yes, what's really fascinating is that it can give off energy. It can give off energy in the visible region of the electromagnetic spectrum. So we can actually see it. You can actually see it. Look over there, you can actually see some of the energy that's emitted. Excitation of this electron, you got to hit it with the right quanta, okay? Not too much, not too little. And then it relaxes back, okay? Relaxes back to ground state. As it relaxes back to ground state, emission, okay? Emission. In any region of the electromagnetic spectrum. So remember, this is happening within the atom. We're not kicking out the electron. Okay, we're not kicking out this electron. This is all happening within our body, within the atom. Okay, the next topic that we was covered in Chapter 7 was electron configuration. So do you guys know how the electrons march? Okay, how will the electrons go marching in? So there's a specific there's a specific manner in which the electrons march. Okay, you can make it into you can make it into sort of a nursery song. Okay, so I'm not going to attempt to sing, but let me just show you the order. Okay, so we have 1s, okay, 1s, 1s2, that would be helium. 1s, what's after 1s? 1s, you should tap your feet. Okay, 1s, 2s, 2p, okay, what's this? 3s, 3p, what do we have here? 3p, 4s. What happens after 4s? 3d, perfect, okay? 4s, 3d, 4p, right? Okay, we call this in the box the n-1 block, okay, also known as the d block. Here comes Santa Claus, here comes Santa Claus. Nope, not falling for that. 4s, 3d, 4p, what's after 4p? 5s, and after 5s? 4d, 5s, 4d, 5p, 6s, right? Okay, now what's coming after 6s? Be careful. What comes after 6s? So what f? This is the n-2 block, also known as the f block. So what comes after 6s? 4f, so we're going to go to 6s, 4f, and then we come back up. Okay, we come back up to where? 5d, 6p, 7s. Okay, what's after 7s? Okay, very good, 5f. Okay, and then after 5f, where do we go? I'm sorry, after 5f we go to 6d, and then from 6d, where do we go? 7p. Okay, so that's the order in which the electrons go. Okay? Alright? So the electrons are going to march in a very, very specific order, in a very, very... By the way, how many electrons can an s orbital hold? 2 electrons, right? Spin up and then spin down. What about P, which has 3 subshells? How many electrons can it hold? Yeah, and the way they march is this way. Okay, 1, 2, 3, 4, 5, 6. Okay, they're going to go spin up, and then they'll pair up. They go spin down, spin down, spin down. So this can hold 2 electrons. This can hold 6 electrons. Finally, how much can the D hold? This has 5 subshells. How many can D hold? 10. 10 electrons is in the D orbital, right? So again, how do they march? How do they go in? Spin up, spin up, spin up, spin up, spin up, and then they pair up, okay? So that will be 10 electrons. So a d orbital, whether it's 3d, 4d, 5d, or 6d, has the capacity to hold 10 electrons. P orbital, whether it's 2p, 3p, 4p, 5p, or 6p, has the capacity to hold 6 electrons. And then the s orbital, whether it's 1s, 2s, 3s, 4s, 5s, or 6s, or 7s, has the capacity to hold 2 electrons. They go spin up, spin down. Right. So knowing how the electrons are going to go in, we can sort of get the electron configuration of some of these elements. Right. So as an example, let's give potassium. Okay, just throwing it out here, potassium. Okay, potassium has 19 electrons. Okay, so how will we get to 19 electrons? Okay, 18, I'm sorry, this is not easy to see. Make sure you bring your periodic table to the test. Argon has 18 electrons. What will 19 be? 4s1. So potassium is going to be argon 4s1. What about potassium plus? Okay, these guys like to be +1, right, in the periodic table. Okay. So why do they like to be +1? Okay, so give me that electron. Here, take this electron. Take this electron. I want to give it away. I want to give it away. Because when it gives away that electron, it becomes noble. Okay? It becomes noble. So the nearest noble gas for potassium is argon. Okay, so that would be a completely filled n equals 3 shell. Completely filled n equals 3 shell. When potassium gives up that electron, it will have 18. It will have the same electron configuration as argon. By the way, we call this isoelectric. Isoelectric means it has the same electron configuration. About something like sulfur S. Sulfur S has, I don't know if you can see it, maybe you can squint. Sulfur has 16 electrons, so what will its electron configuration be? Okay, we're going to get 10 from neon. So we're going to get 10 from neon. Okay, and then where will we go? Okay, 10 from neon. 3s2. Everyone see this? 3p1, 3p2, 3p3, 3p4. So it's going to be neon, 3s2, 3p4. Well, S is not going to be +1. Actually, S likes to be -2. Okay, everyone see why it likes to be -2? You see, if it becomes -2, it will gain 1 electron. And then it will gain 2 electrons to be -2. You see it will have the same electron configuration as argon, its nearest noble gas. So sulfur, give me those 2 electrons. I can have a filled n equals 3 shell. Okay, contrast that with potassium, that 1 electron, that 4s1 electron, be like here, take it, take it, take it. So it's literally like all over. So S-2 will have an electron configuration of argon. Okay. And again, we have another example. Okay, K plus S-2 argon. These are all isoelectric. Okay, same noble gas. Okay, so like that, the electrons are going to go marching and marching and marching. There are a couple of exceptions, so just be careful. Everything is fine and dandy until you reach to chromium. Okay. Everything is fine and dandy until you reach to chromium. And everything is fine and dandy until you reach to copper. silver, and gold. Everything is fine until you reach to chromium, molybdenum, and tungsten. So what happens there? Okay, let's look at chromium. Chromium has 24 electrons. So 24 electrons will fill 18 with argon. Okay, that's 18 from argon. And then it's going to be 4s2, 3d1, 3d2, 3d3, 3d4. But this is not the electron configuration that's correct for chromium. Okay, so what exactly happens? Okay, so if you actually draw this out, s orbital, here's the d orbital. So 4s2, we're talking about chromium here, 4s2, 3d1, 3d2, 3d3, 3d4. So 4s2, 3d1, 3d2, 3d3, 3d4. What happens is that this thing self-promotes. Okay. This seems to happen by itself, okay, on its own, totally on its own. So the correct electron configuration for chromium, again, this is an exception, is going to be argon 4s1, 3d5. Okay, this is one of those weird ones, okay, where they march in accordingly, except here, again, this just happens on by itself. This is a little bit better energy, okay, a little bit more stable. All right. On that same vein, okay, we can say molybdenum right below chromium, molybdenum, Mo, right below molybdenum, right below chromium, molybdenum, okay, is going to be krypton. It's going to be krypton 5s2, 4d1, 4d2, 4d3, 4d4. Now it's going to be 5s1, 4d4. Again, this just happens by itself. Okay, 4d5, I'm sorry. This just happens by itself. And then the same thing with tungsten. Okay, tungsten here, which is right below molybdenum, is going to be xenon 6s2, 5d1, 5d2, 5d3, 5d4. Okay, it's not going to be like that. It's going to self-promote. Again, this just happens by itself. So it's going to be xenon 6s1, 4f14, 5d5. Second set of exceptions happens here at copper, silver, and gold. Okay, so the exceptions, this is what you want to keep your eye on. So let's look at copper for a second. Copper, 29 electrons. Right, so it's going to be argon 4s2, 3d1, 3d2, 3d3, 3d4, 3d5, 3d6, 3d7, 3d8, 3d9. Okay, so copper would be argon 4s2, 3d9. Okay, but that's not the electron configuration. Okay, that's not the electron configuration. What happens here? It's out. 1, 2, 3d1, 3d2, 3d3, 3d4, 3d5, 3d6, 3d7, 3d8, 3d9. And again, this just happens on its own, self-promotion. This goes here. Okay, again, totally on its own, spontaneous. So the correct electron configuration for copper is going to be argon 4s1, 3d10. Okay, self-promotion. We can go one below. Silver, it's going to be krypton Silver Ag is going to be krypton, 5s1, 4d10, and then gold right below silver. And this just happens by itself. It's just more stable that way. It's going to be xenon, 6s1, 4f14, 5d10. So a couple of exceptions to this. Normal pattern of electrons marching in. Okay, the last thing here on this chapter has to do with quantum numbers. If you want to get an address, quote unquote, location of an electron, it's going to be 4 quantum numbers: n, l, m of l, and then m of s. Okay. So let's say I pick an electron here. Let's go to this one right here. Okay, what would be the quantum numbers for this electron? Right. So it's a 3D, so n is going to be 3. Okay, what is L for a d orbital? Okay, it's not 0, which is s. It's not 1, which is p. What will it be for d? 2. Right, so this third quantum number, this is called the orientation quantum number, tells you what orientation, what subshell will it place. So here's how you do that for the third quantum number. The middle one always gets 0, and then you're just going to go from right to left, +1, +2, and then -2, -1. Okay, so you go sequentially. So the one that I circled is in what part of the 3D subshell? -2, and is it spin up or spin down? Okay, spin up is +1/2. Okay, so that is the address of that electron. Okay, so that's how you'll do that type of problem. Okay, how about this electron here? Okay, in the green box? Okay. All right, what is n? 4. Okay, what is L for an s orbital? 0. Okay, if there's no other subshell, there's no subshell for the s orbital, so it's going to be 0. Okay, by default. Is the spin up or spin down? Spin up. Okay, so that is the address of that green box. Okay, quantum number. An address, if we were to give an electron an address. Here's the address for this electron in the 3D slot. How about a p orbital? Are you guys comfortable with p's? How about, let's do 4p. Let's do 5p. Okay, 5p. Electrons in the 5p are being housed in the 5p over here in this area here. So spin up, spin up, spin up, spin down, spin down, spin down. So I'll pick on this one in the black circle. So what would be the 4 quantum numbers or the location for this electron in the black circle? Okay, so what is n? 5. Okay, what is L for a p orbital? 1. Okay, so this is how you're going to do the emps of L. The center always gets 0. And then it goes +1, -1. The center always gets 0. And then you just go in order. Okay, +1, +2, -1, -2, -3. So I circled, and this electron is in the +1 state, or +1 subshell. So 5, 1, because it's a p orbital. It's in 1 here, and is it +1/2 or -1/2? it's minus 1/2 spin down. I did, there's a sort of an attachment to your study guide, so make sure you look at that. Alongside your study guide, I made a couple of Lewis structures that I think are important for this exam, so definitely look at these. All right, so as an example, a couple of them you'll see. NH3, okay, that's called ammonia. HCN, that's called cyanic acid. Okay, ICl3, okay, iodine trichloride. Okay, sulfur hexafluoride, sulfur dioxide. Okay, xenon tetrafluoride. Okay, plus those that you see here that are on canvas alongside your study guide. Okay, so what are we interested in? Okay, so what you guys should focus your attention on would be such things as the molecular geometry. To determine the molecular geometry, you're going to need to bring tables 10.1 and 10.2 to the exam. All right, so make sure you have that available or have that close by as you take the exam. Not something you need to memorize, but definitely you want to bring those two. You'll need them to answer some of those questions. You need to know polarization, whether it's polar or nonpolar. This will be important in chemistry too. Okay, so whether it's polar or nonpolar. And you're going to need to know hybridization. Okay, the mixing of the orbitals, hybridization. Okay, so what do I mean by hybridization? What are your choices here? You can have something that's sp. You can have something that's sp2. Okay, that's 3 bonding. Okay, 2 bonding. Here we have sp3. Okay, 4 bonds. Some of them may be lone pairs. Some of them may be double bonds, maybe triple bonds. Okay, you count everything here. There could be an sp3d. There can also be an sp3d2. Okay, so these are what I'm talking about with regards to hybridization. All right, so I'm not going to do all 6 of these. Okay, and they're all here. Okay, they're all here. That's on blackboard, canvas. I'm sorry. Right. So remember, as an example, NH3. Okay, nitrogen happy at 5, hydrogen happy at 1. We've got 3 hydrogens. 5 plus 3 is 8. Right, so 1, 2, 3, 4, 5. Nitrogen happy at 5. 5 minus 5 is 0. Formal charge on that nitrogen is 0. Okay, nitrogen 1, 2, 3, 3 bonds, 1 lone pair. 3 bonds, 1 lone pair. We'll go to table 10.2. Okay, 3 bonds, 1 lone pair, trigonal pyramidal. Okay, and that is a polar molecule. You can see here how that electron is pulling. Okay, so this is the type of analysis that I want you guys to do for the Lewis structure part. So again, it's all multiple choice, so the answer should be there. Are there any questions on this? Some of this can be tricky. As an example, ICl3. Okay, let's just do that really quickly. Okay, I is happy at 7, halogen. Cl happy at 7, but we have 3 of them. So 28 electrons. So we're going to get 28 valence electrons around ICl3. Okay, so our center atom is going to be I. So we'll do Cl, Cl, Cl. Okay. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Okay, where will 25, 26, 27, and 28 go? 25, 26, 27, 28. So I'm going to put it back on the center atom. Now, why will I do that? Okay, I will do that because of formal charge. Okay, so let's look at the formal charge of this iodine. Okay, count with me. Formal charge. 1, 2, 3, 4, 5, 6, 7. What is iodine happy at? 7. What's 7 minus 7? 0. See? 0 formal charge. ICl3 has 0, no charge, 0 charge. Okay? You'll see if you start putting double bonds, the formal charge will mess up. So you construct this so that you don't get formal charges, because the problem I'm giving you does not have a formal charge. The octet rule for this iodine: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10. That's okay. That's okay. We call that an expanded octet. Alright, so these are some of the Lewis structures that I want you guys to be really, conversant, be very confident in. Also, the ones that are on your study guide in Blackboard. Okay, be confident in them. Okay. In terms of hybridization, polarity, and geometry. Okay. Okay. Wrap-up points on this one here. So we have 3 bonds. 1, 2, 3. 2 lone pairs. So what's 3 bonds and 2 lone pairs? Okay, 3 bonds, 2 lone pairs. Okay, it's T-shaped. The molecular geometry of this is T-shaped. Is this tricky? Okay, so if we're going to draw this in three dimensions, okay, I'll put a Cl here, I'll put a Cl here, I'll put a Cl here like the letter T. I'm going to have this pair of electrons come towards you guys. This pair of electrons go away from you guys, or go away from the paper. And that's one way you can make 3D structure of ICl3. Now, why is this tricky? The trickiness comes from the polarity. Okay, so this Cl is pulling like this. This Cl is pulling down like this. Okay. This Cl on the left is pulling this way. Okay, what about this pair of electrons? It's pulling diagonally. Okay, this pair of electrons is pulling diagonally. Okay, what's the net of this and that? Okay. What I want to tell you guys is that the net of this and that, you add them up, it's going to be this way. Okay, the net of this one, number 1, and that one, number 2. So the correct answer in terms of polarity, this is polar or non-polar. Okay, the correct answer is going to be non-polar. Pulling up, that Cl is pulling down, this Cl is pulling this way, this pair of electrons pulling at an angle, this pair of electrons pulling at a down angle, the sum of this versus the sum of that, they kind of build on each other, is going to be this, okay? Which cancels out that, so it's a non-polar molecule. The quick inclination is to think this is polar, but ICl3 is not polar, it's non-polar because they all cancel each other out. Consider something like water. Okay, that's definitely polar. Okay, here's the water molecule. Oxygen is pulling this way. Oxygen is pulling that way from this hydrogen and that hydrogen. So they're kind of building up. These guys are building up, okay? Well, these guys are building up, but when you add them up, that addition gets canceled out by the Cl pull on the left. So, yeah, it's a little bit tricky for this one. And finally, 3 bonds, 2 lone pairs. Okay, 3 bonds, 2 lone pairs. That's going to make this 5. 3 plus 2 is 5. So sp3 Okay, 3 plus 1 is 4. 4 plus 1 is 5. So this is an sp3d hybridized iodine. So like that, I'd like for you to do that for all of these as well as all of these that are potentially could be on your exam. I think there's a second page here. Yeah, one. Right, so check that out and make sure you're confident in all of these. Right, the last part of the exam has to do with trends in the periodic table. Part that I want to tell you about the last 5 or so minutes is periodic trends. Take our skeleton periodic table. The trend that I want you guys to know is the trend of ionization energy. Okay, ionization energy just means the energy to kick out an electron. Okay, you're hitting it with enough quanta that the electron is gone. It's ejected. Okay, so it's the energy to remove an electron. The trend, the general trend, there's always going to be exceptions. The general trend is this. Okay, if you go from left to right in the periodic table, it's called a period. The ionization energy actually increases. It takes a lot more energy for me to get an electron out of these guys, especially here because these guys really... Right, so talk about the noble gases which have a complete shell. Okay, they're not going to give up their electron. But the ionization energy actually decreases as you go down a group in the periodic table. Okay, outer, 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 outer. Okay, it's easier to get an electron that's over out there to just kick out. Right, so that's one trend. So, you know, if you have something over here, an element versus an element over here, this will have a larger IE1, ionization energy. It takes a lot for you in terms of energy to get an electron out of this guy as opposed to this guy. So that's one trend. Okay. Let me give you a second trend here. And trend here is atomic radius, or literally the size of the atom. We're talking about how big the atom is. These guys over here are actually pretty big because they have that electrons here. Take this electron, take this electron, take this electron. They want to give that electron, so that electron's all the way out there, ready for the picking. So the size actually increases going this way. We're talking about atomic radius. Increases in this directionality across a period, and it increases in this directionality down a group. So again, something like here, okay, some element over here versus an element over here. On this one would be smaller. Okay, I'm talking about in terms of size. In terms of ionization energy, this one would have a larger ionization energy than size, ionization energy, how they are sort of organized in the periodic table. There's definitely a trend. Okay, across a period, we call this a period, and then down a group. There's certain trends that we can get from the periodic table. I think I will just end it here. We are approaching the end of class anyways, so thank you all for a good semester. Even though we're having a public health crisis, and you do not have to come on Tuesday. And thank you. Okay, best of luck. I think I'll see you next year. So.